So this video is going to be a solution to the first exam that we had. I'm just going to go through quickly for how to solve these problems. So the first problem is kind of two parts where we are finding what the force is on this charge Q right here, which means we need to find the force that our capital Q is acting on this. So this is the force capital Q acts on this, as well as the force that is acted on it from this distribution of charge right here. So I'm going to call this F vector sub lambda comma Q. Okay, so let's first start by finding what the force is that capital Q is acting on lowercase q. And what we can say is that the total force of total is going to be equal to F vector sub capital Q comma Q plus F vector sub lambda comma Q. Okay, just put some commas in there. So first thing that we need to do when we're doing this is to write down the general equation that we're going to use. So F vector 1, 2 is going to be equal to 1 over 4 pi epsilon naught Q1 Q2 divided by R squared times R hat. And we're going to need to determine what is R hat. And so looking at this for R, this is the distance from the charge Q to the charge capital Q. Okay, so this is going to be R. So this distance right here is a distance of A. This distance right here is going to be a distance of B minus H, because this distance here is going to be B. This is the distance of H. So then we can say that R is going to be equal to the square root of, this is going to be B minus H quantity squared plus A squared. Now, to determine R hat, we say that R hat is going to be pointing like this. I can define this angle of theta. And so we can say that R hat is going to be equal to minus cosine of theta x hat minus sine of theta y hat. Now, we need to determine what cosine and sine of theta are because theta is not a given parameter. And we can use the triangle that we built here in order to do that. So we can say that cosine of theta is going to be equal to the adjacent, which is going to be A, divided by the hypotenuse, which is R, times x squared, or times x hat, minus the sine of theta, which is going to be the opposite, which is going to be B minus H divided by R times y hat. So what we can see then is, moving over here, that F vector Q comma Q is going to be equal to 1 over 4 pi epsilon naught lowercase q times capital Q divided by R cubed, which is going to be, this is going to be H, this is going to be B minus H, although it doesn't matter because it's squared, B minus H quantity squared plus A squared to the 3/2 times negative A x hat plus, this is going to be minus B minus H times y hat. Okay, so that's the first force that we need to find here. The second force that we need to find comes from the distribution of charge that we have here. And the way that we're going to do that is we're going to say that dF is going to be equal to 1 over 4 pi epsilon naught times Q times dQ divided by R squared times R hat. And really what we're doing here is essentially the same thing, only we have some infinitesimal charge dQ that we need to define. So this infinitesimal charge dQ is going to be equal to lambda times dl, where lambda is some given function. So this is lambda as a function of x, is going to be equal to beta x to the 4th times x squared plus h squared to the 3/2. And you'll remember on the exam I made an edit here that this is going to be h squared. Okay, and dl is going to be the infinitesimal length that this charge is spread over. This is along the x-axis, so this is dx. Now, to find r here, here's r. This is the distance of x. It's going to be some arbitrary distance because each one of these dq's is going to be a different distance from the origin along the x-axis. And this is a fixed distance of h. So r is going to be equal to, I'm running out of room here, but I'll write this over here now. R is going to be equal to the square root of x squared plus h squared. Okay. Now we need to determine what r hat is. So here's some angle of theta, or we can call this phi because I used theta already. R hat is going to be equal to cosine of phi times x hat with a negative sign, plus sine of phi times y hat. And going back to this triangle that we have, cosine of phi is going to be equal to x divided by r, and then sine of phi is going to be h divided by r. This is y hat. Now, putting all of this together, we end up seeing that f vector lambda comma q is, and that's a lowercase q, lambda comma lowercase q is going to be equal to 1 over 4 pi epsilon naught times the integral. Now, when we're integrating this, we want to think about where are we starting, where are we ending. This charge distribution begins at x is equal to 0. It goes up to x is equal to L. So this is going from x is equal to 0 to x is equal to L. And then we have a q, which is going to be our lowercase q, times dq, which is going to be lambda dl. In this case, lambda is going to be equal to beta x to the 4th times x squared plus, this is h squared to the 3 halves times dx divided by. Now we can group these r's together. And so when we group the r's together, we're going to have an x squared plus h squared to the 3 halves. And then this is going to be multiplied by negative x hat plus h y hat. Now you can see why I chose lambda the way that I did, because this lambda is going to cancel this r cubed in the denominator. So this is going to make the calculation much easier. So grouping some terms together, we're going to have, this is going to be q beta, and then divided by 4 pi epsilon naught times the integral of x to the 5th x hat plus x to the 4th times h times y hat times dx, integrated from 0 to L. And when we do this integral, we end up finding our final answer for f sub lambda comma q. This is going to be equal to q beta divided by 4 pi epsilon naught times L to the 6th divided by 6 times x hat plus h L to the 5th divided by 5 times y hat. And then adding those two forces together will give us the final answer. You didn't actually have to explicitly write this line where everything's added together. You just needed to find each one of these forces individually and then say that the final answer is equal to the sum of the two. Okay, so the next question is finding what the electric field is at the center of this arc of charge. And I gave you a hint here, and that hint was to say that it's easier if you're defining your angle relative to the negative y-axis. So the first thing I'm going to do is I'm going to draw what I meant in there. So our electric field, in principle, could point like this. It's actually pointing the opposite direction because it's a negative. But the point here was that this can be defined like this. Here's our angle of theta. Okay. So the reason why we do that is we are going to say that dE vector is going to be equal to 1 over 4 pi epsilon naught dq divided by r squared times r hat. The way these problems always go, we have our three things to find. 1, 2, 3. First thing that we find is what dq is. In general, this is going to be lambda dl, where lambda, by definition, is going to be the charge per length. We have an arc length of, we have a charge of minus 5q divided by the arc length here, which is going to be r times alpha. And dl is going to be r d theta. Okay. Now, the next thing that we need to do is we need to find what r is. This one is very straightforward because this is going to be the arc of a circle. All of these points are equidistant from the origin, which is what actually defines a circle. So this is going to be the radius of capital R. Now, the last thing, and this is why it's essential to define this angle the way that we did. So we're saying that our r hat, for the way that I define this, it has some component. So here's our angle of theta. This has some component right here that is a sine of theta in the x direction, sine of theta x, this is an x hat, and then some component here that is a cosine of theta in the y direction. So this is going to be plus cosine of theta times y hat. Okay, so to find our answer here, we just need to put this together and integrate. So what we're going to have is E vector is going to be equal to 1 over 4 pi epsilon naught times, I'm going to factor out what lambda is. So this is going to be, and then cancel an r. So I'm canceling this r and that r implicitly when I'm writing this next line. So this is going to be minus 5q divided by alpha times the integral. Now for our integral, we're integrating over theta. So we want to define where theta begins and where theta ends. So this is going to be theta is equal to 0. So that's going to be when this is exactly vertical. And then this is going to go all the way around to theta is equal to alpha, which is there. So this is going to go to theta is equal to alpha. And then we can plug in the rest of what we have here. So we have a d theta times a sine of theta x hat plus a cosine of theta times y hat. And we're missing an r squared here. So I'm just going to put the r squared right there. All right. So when we do this integral, the integral of sine is going to be negative cosine. So this is going to be 1 over 4 pi epsilon naught minus 5q divided by r squared times alpha. This is going to be minus cosine of theta x hat. And then this is going to be plus sine of theta times y hat, evaluated from theta is equal to 0 to theta is equal to alpha. And so the final answer that we have, I'm going to group a couple of things together here, is going to be, this is 1, so this is minus 5q divided by 4 pi epsilon naught. That's a funny looking epsilon there. 4 pi epsilon naught times r squared times alpha times, this is going to be 1. This is 1, yeah. So this is going to be 1 minus cosine of alpha times x hat plus sine of alpha times y hat. Okay. And what I did here was I flipped the order of this and absorbed a negative sign. Okay, so that's our answer to the second one. It's our second problem. All right, third problem has 2 parts. So this one, you're imagining some strange universe where the force between 2 charges is given by F vector 1, 2 is going to be equal to Q1, Q2 times alpha times plus beta R plus gamma R squared times R hat 1, 2. So that's like, imagine you have a charge here, charge there, Q1, Q2. This is the force that Q1 acts on Q2. But we're going to say that the connection between the electric field and the force is going to maintain the same structure that it does in our universe. And that's to say that the force is going to be equal to Q times E. And so that being the case, we can say that the electric field E vector is going to be equal to, from just some point charge Q, is going to be the same thing with only 1 charge instead of 2. It's beta R plus gamma R squared. Now, if we want to find what the electric potential is here, then we say that the electric potential, V, as a function of R, is going to be equal to the negative integral of E dot dl, where dl is going to be, I missed a r hat there, dl vector is going to be r hat dr. Okay, so what we can do is we can plug this guy right here into this equation, and what we end up finding is that v as a function of r is going to be equal to q alpha times r plus beta r squared over 2 plus gamma r cubed over 3. And this is a scalar quantity, it's not a vector quantity. Okay, so that's the first part. Now, the second part, because what this question was doing effectively is you're going from electric field to electric potential. I want to go backwards with the second question. And so with the second question, this says you're given some electric potential, where this electric potential V is a function of X. Am I missing a negative sign there? Yeah, I'm missing a negative sign. There's a negative sign right there. So V is a function of X and Y is going to be equal to alpha X to the fourth Y squared plus beta Y cubed. And we want to find what the electric field is going to be. Now, if I have an electric potential and I want to go to an electric field, the way that we do that is we say that the electric field E vector is going to be equal to the negative gradient of the electric potential. Since this is written in terms of X and Y, that means that we want to write this gradient in terms of Cartesian coordinates. And so this says that this is going to be X hat partial derivative with respect to X plus Y hat times partial derivative with respect to Y. And this is going to be acting on our electric potential, which is going to be alpha X to the fourth Y squared plus beta Y cubed. Okay. Now, when we operate this negative gradient on this, what we're going to find is that the electric field E vector is going to be equal to X hat times 4 X cubed times Y squared with a negative sign minus Y hat times 2 alpha X to the fourth Y plus 3 beta Y squared. Okay, so that's our electric field from this electric potential. So from those two questions, you're seeing how do I go from electric field to electric potential, and how am I going from electric potential to electric field. Now, the last question that we have here, we have a box that we want to find what the flux is through all 6 of the surfaces. So what I'm going to do is I'm going to label these. So the top surface I'll call T. The back surface I'll call B sub A or BA. The front surface I'm going to call F. The bottom surface I'm going to call BO. The right surface I'll call R, and the left surface I'll call L. And so what we want to find is the flux here, the electric flux, which is going to be equal to the integral of E vector dot dA. And this is a double integral because it is over an area. Single integrals over lines, double integrals over areas, triple integrals over volumes. So here, let's start with finding what the electric field is out of the top face. So phi sub top is going to be equal to the integral of E vector dot dA top, and dA top is going to be equal to Z hat times dx dy, right? The vector that points perpendicular to the surface is in the z direction, and the little pieces that form this area are in x and y. Okay, so now what we do is we take the dot product between this and our vector, and when we do that, we're only going to pull off the z term because z hat dot z hat is 1, z hat dot y hat is 0. So this is going to be the integral. This is going to be the equal to the integral of beta h minus z times dx dy. And in principle, we would have our limits of integration for x. X goes from 0 up to w, and y goes from a to a plus L. Okay. But we have to be careful here because we need to evaluate what Z is, because this entire surface up here is going to have the same value of Z, and that value of Z is H. So we need to evaluate this integral for Z is equal to H. And when we do that, we have H minus H, which is 0. So our flux out of the top, so it's like phi sub E top, just to be clear with my notation, that's not phi, it's not the flux of some field T. It's the flux of ET. So this is going to be equal to 0. Okay. Now we can do the same thing with the bottom. Phi sub BO. This is going to be equal to the integral of the E vector dotted with the dA from the bottom, where dA bottom is really the same thing as dA top with a negative sign because it's pointing in the opposite direction. dx dy. Okay, so now what we have is we have beta times h minus c with a negative sign out front, dx dy, and this is going to go from x is equal to 0 to x is equal to w, y is equal to a to y is equal to a plus l, and we're evaluating this for z is equal to 0 because this bottom surface, every point on here has a z value of 0. So when we do that, we end up finding that this term is going to go away. We're integrating effectively a constant in x and y. So this is going to end up giving us at the end of the day something that looks like this. This is going to be minus beta times h times w times l. Because when we evaluate these limits in y, it's going to be a plus l minus a. So that gives us just an l. Okay. So that's our bottom face. Okay. Now let's look at our front and our back face. So when we're looking at this, the dA for the front is going to be x hat dy dz. But our electric field does not have a component in the x direction. So that tells us that that dot product is 0. So our phi sub f, the front face flux, is going to be 0. And the same thing for the back, because this one is going to be minus x hat dy dz. And so phi sub back is equal to 0. So we only have two left. This is going to be the flux for the left. So phi sub L. This is going to be equal to the integral of E vector dot dA left, where dA left is going to be minus y hat times dx dy. And so this is going to be equal to the double integral of this function in y is going to be alpha x squared y times d, sorry, this should be a d, this is a dx dz, sorry, this is a dx dz. So this is a dx dz, dx dz, okay? Where we're evaluating this for y is equal to a, because that's where the left face is. Left face, all of the values of y are just going to be a. And this is going to go from x is equal to 0 to x is equal to w, and z is equal to 0 to z is equal to h. And so this says then that our flux out of the left surface is going to be, we have a negative sign here. So this is going to be minus alpha w cubed over 3 times h times a. Okay. Ha. Okay. So now the last one, phi sub r, this is going to be equal to the integral of E dot dA, where dA sub r is going to be y hat times dx dc. And again, we have something very similar, barring the negative sign and barring the value for y. So this is going to be alpha x times, this is x squared, times y dx dz without the negative sign, because this negative sign came from this dot product with this dA. So this is going to be from x is equal to 0 to x is equal to w, from z is equal to 0 to z is equal to h. And then when we evaluate this integral, this is going to be alpha w cubed over 3 times h times a plus l. Okay. And then what we saw here was of the 6 surfaces, only 3 of them have some non-zero flux. Okay. So that's it for this exam.